So today in this video, we're going to be learning about the angle bisector theorem. So this rule is typically used in geometry problems in Math Olympiads. So hope you learn a lot from this video. And so let's start. So we have this triangle here where we have this triangle ABC here, where line C, where D is a point on AB, such that line CD is an angle bisector of angle C or angle ACB. So what I mean by an angle bisector what an angle bisector is that it's a line that bisects an angle. So it divides the angle into two equal angles. So it divides the angle in half. So here CD is an angle bisector of angle C because it's dividing angle C into two equal angles, BCD and ACD. So here CD is an angle bisector of angle C. So now we know what an angle bisector is. So let's get on to knowing the theorem then. So let's label the length of side BC as small a, and the length of AC as B, and the length of BD as X, and the length of AD as Y. Then the angle bisector theorem states that, let's put that in pink to emphasize on it. The angle bisector theorem states that the ratio of A to B is equal to the ratio of X to Y. And that is the angle bisector theorem. But why does this work though? So why does this work? So now I'm going to show you the proof for this rule. So this rule basically tells you that if you have this kind of triangle where there's an angle bisector like this, then the ratio of this length to this length is equal to the ratio of this length to this length. So just keep that in mind. So this rule will be useful when you see these kind of shapes or you see an angle bisector. So yeah. Okay, let's move on to the proof. So here I'm going to draw a line that passes through point A and is parallel to line BC. So let's draw a straight line that passes through A and is parallel to line BC. That's about right. Wait, let's make that a bit longer. Oops. That's about right. Okay, never mind. So here we drew a line that passes through A and is parallel to line BC. And now we're going to extend CD so that it meets this line. So we're going to extend this. Ooh, it matches it there. Just right. Okay. So here we have an extension of line CD and a line that passes through A and is parallel to BC. So we have some imaginary lines here. And we're going to be using these to gain some more information and derive this equation. So first let's first name this point E, and we're going to name length AE as Z. So here we can see that angle BDC is equal to angle ADE. So angle BDC is equal to angle ADE because you can clearly see that they are vertically opposite lines because line CE and line AB is clearly straight lines. So we found two equal angles. And if we do more angle chasing, we're going to find that since line BC and line AE are parallel, we see that angle BCE and angle AEC are alternate angles. They're alternate angles, which means that angle BCE is equal to the measure of angle AEC. So angle BCE, this dot, is equal to the angle AEC. So let's mark that there. So you got that. Oh wait a sec. Let's mark these angles aren't equal to these angles. So we're gonna put them as different symbols. Yeah, sorry about that. Okay, so we've done some angle chasing and found some congruent angles, and we're gonna use these to find some similar triangles now. So let's change our ink to black first. Okay, so we see that angle BCE is equal to angle AEC and angle BDC is equal to angle ADE. So 2 of the interior angles of triangle BCD is equal to 2 of the interior angles of triangle AED. And this conveys that triangle BCD is similar to triangle AED. So triangle BCD similar, is similar to triangle AED. Okay, wait a sec, I'll just make that similarity symbol a bit neater. There you go. Yeah. So triangle BCD is not congruent. Similar to triangle AED. So what does that tell us? So this tells us that the ratio of BC to the ratio of length of AE is equal to the ratio of BD to the ratio. I'll start again. So this tells us, the similarity tells us that the ratio of the length of BC to the length of AE is equal to the ratio of the length of BD to the length of AD. So let's write that down. The length of BC to AE is equal to BD to AD. So we know the variables that represent these values. So let's write them down. So BC is equal to A, and AE happens to be equal to Z, and BD, where's BD? BD is equal to X. And AD is equal to Y. Okay, so we're almost done now. We're getting really close to our formula, but why do we have to Z? Well, we have this variable Z though. What are we gonna do with this? So we have to look at this diagram more closely and find some more facts about it. So here we see that angle ACE is equal to the measure of angle AEC. So this means that triangle ACE is an isosceles triangle where the line where side AC is equal to side AE. So B is equal to Z. So we can just substitute B into Z, which gets us that A to B is equal to X to Y. And we get our formula. Oops, that arrow is... and we get our formula. So we just proved the angle bisector theorem. So in this video, we learned about what the angle bisector theorem is, and we also proved it, so we know why it works. So yeah, in the next video, we're gonna be using this theorem to actually solve a geometry problem, and it's pretty interesting. So hope you enjoyed this video, and see you in the next one.